In our first situation, we have a 5 kilogram ball moving at 7 meters per second. Let's let this be the positive direction. Here goes the ball moving at 7 meters per second. Meets an 8 kilogram ball, which is moving at negative 3 meters per second. So this ball's moving faster than this one. This one's faster than this one. In the collision, the first ball slows down to 4 meters per second. So it's going 7 meters per second, and 7 meters per second slows down to 4 meters per second as a result of the collision with the 8 kilogram ball. Now, the first thing we want to find is the change in momentum, and therefore the impulse on the first ball. So let's think about that. First place, you know that the net force in an object multiplied by the time interval is the change in mass times velocity. And the change in mass times velocity is mvf minus mv naught, which could also be written m times vf minus v naught, or m delta v. Now, for the first ball, the change in mv is from 5 kilograms times 7 meters per second to 5 kilograms times 4 meters per second. That's a change of negative 15 kilogram meters per second. Okay, again, 7 meters per second, the initial, 4 meters per second, the final. It's going to slow down, it's going to lose momentum, it's going to lose 15 kilogram meters per second of momentum. So, the average force times delta t on the first ball by the impulse momentum theorem, and I should say the average net force, and I am missing nets on a lot of these, so let me insert that. Okay, again, since net force times delta t is change in momentum or change in mv, F1 net delta t is negative 15 kilogram meters per second. The impulse, F net delta t is impulse. The impulse of the average force of the force acting on the first ball is equal to change in momentum, F1 net delta t, negative 15 kilogram meters per second. So the F1 net, and we got an F1 net bar indicating the average force, because in a collision of two balls, the balls will collide and collapse and then rebound. The force in that process is quite variable. It increases up to a maximum and then decreases back to zero as the balls move apart. So we have to talk about the average force. We're not talking about maximum force, but some kind of an average force. Okay, the average force then on the first ball is negative 15 kilogram meters per second divided by 0.02 seconds. So I've got smudged here. And we divide that out, we get negative 750 kilogram meters per second squared, which is negative 750 newtons. Then the question is, well, what happens to the second ball? Well, by this analysis, the average force on the second ball is equal and opposite to the average force on the first. That's just from Newton's third law, action-reaction. The balls exert forces on one another, and those forces are equal and opposite, so that the change in momentum, m2, excuse me, delta v2, the mass of the second ball times its change in velocity, is equal to F2 net delta t. F2 net is equal and opposite to F1 net, so F2 net is plus 750 newtons. Multiply that by 0.2 seconds, you get plus 15 kilogram meters per second. So the 8 kilograms, the mass of the second ball, multiplied by delta V2 is 15 kilogram meters per second. So delta V2 is, well, easily solved. We get plus 1 7/8. Now these figures aren't all significant, but that is 1.875 meters per second, and I've included all the numbers there just so we can check to see that this works out exactly. Unless otherwise stated, we regard all these quantities as completely accurate. So this is kind of an ideal case where we have exactly 5 kilograms, exactly 8 kilograms, exactly 7 meters per second, in which case we would end up with exactly 1.875 meter per second change in velocity of the second ball. Now, of course, we could add that one. Well, we did here. I didn't see it. Okay, our new velocity of the second ball is our old velocity plus the change in velocity. So our new velocity, our velocity after the collision, is going to be our original -3 meters per second plus our 1.875 meters per second, giving us -1.125 meters per second. Now that's the solution using the impulse momentum theorem. There's another way to solve this, and that is to say that, well, since the forces exerted are equal and opposite and they act for the same time, then the impulses are going to be equal and opposite as they were here. We have the -15 kilogram meter per second impulse on the first ball, the +15 kilogram meter per second impulse on the second. The total momentum before, and let me adjust the camera so we can see this. Okay, because the impulses are equal and opposite, the changes in momentum of the two balls will be equal and opposite. If these balls are in an isolated system, that is, there are no forces acting on the balls other than one another, and that's our assumption over here, the total momentum before then has to equal the total momentum after. Since one ball is going to lose momentum and the other ball is going to gain momentum, and the loss is exactly equal to the gain, that tells you that there's no change in the total momentum. And we could write that then in the familiar equation, m1v1 plus m2v2 equals m1u1 plus m2u2. Just the equation you want to give somebody without any development if all you want them to do is plug into equations and not have any deeper insight. Okay. So this equation is not primary. Impulse momentum is primary. This equation follows from impulse momentum, and we do the analysis by impulse momentum first. We get the same result though if we use this equation, and this equation just embodies impulse momentum. So before collision, you have mass 1 moving at velocity v1, mass 2 moving at velocity v2. And after collision, it's mass 1 moving at velocity u1, mass 2 moving at velocity u2. So your m1v1 and m2v2 are the momenta of the two objects before collision, m1u1, m2u2, the momenta after collision. Okay, well, in this case, m1 and m2 are 5 kilograms and 8 kilograms. Velocity 1 is 7 meters per second. Velocity 2 is -3 meters per second. Those are before collision. Then after collision, u1 is 4 meters per second, and u2 is unknown, and that's the quantity we want to find. Now, we've already found it is going to be -1.125 meters per second, and I'm not sure that's visible anymore, but you see that we're going to get it again anyhow. And, of course, that was explained before I readjusted the camera. Okay, so we just plug this information into this equation and everything is going to come out. Well, plugging it in, I'm not going to read it to you, but here's M1, here's V1, here's M2, here's V2, here's M1 and U1, excuse me, and M2 and U2 being expressed as a symbol. So we're going to solve for U2. Okay, well, that's very easily done. We can multiply all this out and add it up, and as before, we're going to get, actually, I say as before, no, we're going to get something new. 5 times 7 is 35, 8 times -3 is -24, 35 and -24 is 11. Both these quantities have units, kilogram meter per second, so it is legitimate to add the numbers, and of course we carry along the units. And then we multiply this out, we get our 20 kilogram meter per second for the after collision velocity of the first ball, the after collision momentum of the first ball, 8 kilograms times U2 for the after collision momentum of the second ball, and that's equal to the total before collision momentum of the two balls. Then we subtract the 20 kilogram meter per second from both sides and divide by 8 kilograms, and I've just done that in one step, and we get -1.125 meters per second in complete agreement with what we get when we add the negative 3 meter per second velocity of the second ball, the initial negative 3 meter per second initial velocity of the second ball, to the 1.875 meter per second change in its velocity. Just a quick note, in the calculation in the analysis by the impulse momentum theorem, it might seem that we needed this 0.02 second time interval to complete the calculation, and that it might be different if there was some different time interval. So it's not completely clear that this follows from this, or that this will always be equivalent to this, but let's just note that all we need to get from here to here is this. We don't need to figure out the average F1 or the average F2. We know that M2 delta V2 equals F2 net delta T, and that F2 net delta T, we don't have to calculate it from 750 newtons plus 0.02 seconds. We know that since F2 net is equal and opposite to F1 net, that F2 net delta T is going to be 15 kilogram meters per second. So we can go directly from here to here to here. And we can just completely bypass any of the calculations of the actual forces. I included those calculations to convince you that there is an actual force there. And if we know the time the balls are in contact, we can figure out what that, at least the average force is, but not necessary for the derivation or for the equivalence of these two ways of solving the same problem. So if you were asked to solve this problem without using this equation, you would use the impulse momentum theorem, or if you were asked to solve it using the impulse momentum theorem solely, the analysis would be exactly the same down to this point. You wouldn't bother calculating F1 net or F2 net. You would simply know that M2 delta V2 is F2 net delta T, and F2 net being opposite F1 net, the M2 delta V2 is going to be, well, the F2 net delta T is going to be the opposite of what you have up here, and you then continue.